This kind of unification is, in a certain sense, every theoretical physicist's dream. It is your goal as a physicist to try to take a disparate phenomena, bring them together, and realize it's all just one basic set of ideas. Newton did this, and did it in perhaps the most profound way. He said that what is happening here on Earth with the marbles rolling down lamps in Galileo's experiment is really the same fundamental physics as the Earth going around the Sun or the Moon going around the Earth. It's all the same. It's all F equal ma. Now, Maxwell has done this again. Everything that is electrical, everything that is magnetic, everything that is optical, it's all really ultimately just these Maxwell's equations. He has not only done this wonderful service to the field of physics, but also to open up new branches of physics, because now you can think about what might be called physical optics. You can think about optics in a new way, instead of thinking about the path of the rays of light through a prism or how a telescope might focus the light. You can also think about the interaction of the light with matter. It's just electric and magnetic fields interacting with charges in the matter. It's really all explainable by Maxwell's equations. Light had been studied forever. The Greeks were thinking about light. Isaac Newton was thinking about light. Many physicists have been curious about light. I'd argue that Newton's career as a physicist began with his experiment on the prism and the colors of the light. Newton's recognized that white light was really composed of all of the colors in the rainbow, and Newton's had a background working the theory of the light, which was that light was corpuscular. It was made of little light particles. If you have a light bulb, Newton was thinking that the light bulb is spewing out a bunch of little light particles in all directions. They travel outwards at the speed of light, and so Newton would think that when they hit your eye, it's some sort of the F equal ma things where they're bumping into this retina in the back of your eyeball. He just has this different mechanism to think about light. Yes. It turns out it didn't really matter so much because he wasn't paying much attention to the wave-like nature of the particle-like nature. It was just his belief, but the experiments that he was doing had to do with other aspects of light, like the color of it. At the time, the technology didn't really exist for Isaac Newton to convincingly prove to anybody, including himself, whether or not light was a bunch of little particles or light was some sort of the undulation, some oscillating phenomenon. There were lots of theories. People were arguing with Newton's back in his idea. In his era, and it took until 1800 when a physicist named Thomas Young finally did an experiment directly with light to prove convincingly to the world that light is a wave phenomenon. We'll talk about that in a later lecture because Young's experiment is a little bit complicated, and it's really part of our broader story that we need a little bit more time to go into, right? Young showed that light was a wave. This is 1801. Maxwell is not going to do his theory for another 60 years. So for 60 years, the whole physics community is wondering what the heck is waving. Light is waving, but what is waving? When we think of waves, we think about water. We think of some material object moving up and down, and nobody had any clue what could be waving. Maxwell answers the questions. It's a new thing. It's an electric field that is waving. Electric and magnetic fields are moving. They are changing in the strength and in the direction. There are no material objects moving at all. The wave is a wave of electric and magnetic fields themselves. It's a wild idea. It's a little bit abstract. Again, you can recognize why it would be difficult for people to just accept this instantly, but it turns out to be enormously practical. That's right. So, think about lenses and how they focus light, or think about rainbows. Think about the colors that we see from the light, or think about the prism. Think about diffraction of the light as it goes through a very narrow hole and spreads out. All of this can be described in the Newtonian era. They can be described, but they cannot be fundamentally explained until we come to the Maxwell and Maxwell's equations. Maxwell tells us that light carries energy with it. It's a part of the equations. When you wiggle the electric charge here, you are doing work on it. You are applying a force. You are accelerating it. It's moving over some distance. Force times distance is work. So you are doing work on the charge. Wow! Whatever you do work, that means you are transferring energy. Wow! Where is the energy going? Conservation of law, it's spreading out in this electromagnetic wave. Electromagnetic waves can carry energy. Well, we know that. Light can carry energy. Light from the sunshine carries solar energy with it. And so all of a sudden, there is a whole new bunch of technology that is available to us. Electric light sources and electro-photovoltaic panels. Although there is a little bit more quantum physics involved there. Fundamentally, the source of energy is pure classical Maxwellian physics. Classical Maxwellian physics. Wow, Newtonian physics and Maxwellian physics. Wow. You are thinking about Maxwell's equation, and remember the speed that he came up with. 186,000 miles per second, the speed of the light, turns out is a number that is independent of any details of the motion. Wow, Maxwell thought really hard about this. What if you jiggle faster? What if you jiggle in a circle? What if you jiggle faster and slower in the funny pattern? You will produce different ripples in the electric and magnetic fields. They themselves will wiggle at the frequency that you wiggle the electric charge. If you wiggle twice as fast, the electric field will respond twice as fast, and the receiver, if you have one, the electric charge far away will wiggle matching the original one. Wow. The speed at which this traveling wave spread is always 186,000 miles per hour second. The speed of light. That's a fundamental property of the light. What is the difference between the different kinds of light? Okay, wait. What is the difference between the blue light and red light? All of a sudden Maxwell will say, oh, I have it. Red light and blue light don't differ in their fundamental properties. They are basically the same exact thing. It is just that blue light arises when your retina wiggles faster. Red light is what you perceive when your retina has electron in it that wiggles a little bit more slowly. There is this range of the wiggle frequencies where your human brain can detect this electromagnetic wave. What if you wiggle a little bit faster than what makes a blue signal to your brain? There is still an electromagnetic wave. It's still traveling in exactly the same way. It's the same physical things, but you will not perceive it anymore. It's beyond the violet. It's ultraviolet, and you would need some new detector that could detect this ultraviolet radiation. Sometimes I call ultraviolet radiation ultraviolet light because even though I can't see it, I think of it as the same things as the light. It's going to go through the lenses. It's going to do all the sort of the things that light does. Wow! Ooh, so if you go even faster still and wiggle your original charge faster than the ultraviolet, you move up into the kinds of the electromagnetic radiation such as X-rays. X-radiation is just electrons wiggling even faster, still producing a wave that is wiggling even faster still. Beyond the X-rays are gamma rays. X-rays are what the dentists use to imagine your teeth. The idea is that it's just a light coming out of the X-ray machine. It's an X-ray light. It's a different frequency of the light. And when that light strikes your body, it turns out it's wiggling fast enough that it can travel through much of your body. Most of the watery parts of your body are transparent as glass to this particular frequency, this particular color of electromagnetic radiation, right? So your bones are dense enough that will absorb this light, and so the picture that you see, it's a shadow picture. It's just like any shadow picture of light, except that you need a different detector. Your eyeball cannot detect X radiation. What if you go in the other direction? What if you wiggle slower than the lead? You have an infrared. Infrared radiation arises from the warm object because warm objects have wiggling electrons in them. Wow! And they produce this electromagnetic radiation. It again is another form of light, and we can build cameras, night vision cameras that detect that radiation. You simply need some electric circuit that respond in that frequency range. Wow! So you simply need some electric circuit that respond in that frequency range. Wow! So cool, so cool. In honor of Heinrich Hertz, we've named the unit of frequency the Hertz. 1 Hertz means 1 wiggle per second. Wow! 1 wiggle per second. The electric wall plug in your house is 60 Hz. It means that electricity is sloshing back and forth 60 times a second. The light that your eyeball is sensitive to, the visible light, would be about billion Hertz. That's how many times per second electrons have to wiggle in order for your biological retina cells to produce an electrical signal to your brain. Yeah. I learned it. At medical school. If you go beyond the infrared, you are into the microwave radiation range. There are just names that people have given to the different frequency bands. Microwaves in your oven are nothing more than another kind of light. It's just electromagnetic radiation at a much lower frequency. It happens to be the frequency at which water molecules like to jiggle, and so this radiation tends to make water molecules wiggle back and forth, then heat up your food. Wow! If you go even lower in the frequency still, you are down to what we call radio waves. The radio waves that are being broadcast are just a big antenna somewhere with an electron that goes up and down at that antenna. An electromagnetic wave that travels out and reach your antenna, and the electrons at your house go up and down. It's just a Heinrich Hertz experiment all over again. The only reason you need to plug in your radio is to amplify the signal. Wow! You take your speakers and make that oscillating signal push the speaker in and out at some frequency. You need to change the frequency so that it's even lower still, so that it produces a wave that your ear can detect. We'll talk about that in the next lecture. Wow. So, in the end, you can see that Maxwell's equations are not only leading us to the new physics, they are also leading us to many new applications. Maxwell has helped create the field of applied physics, and he has also opened up a whole new way to study optics and light. Wow! Think about television sets, cell phones, garage door openers. They are all Maxwell's equations, and what I want to do now is to think more about waves in general. Now we see how important waves are in the electromagnetic world. We realize that the waves are important everywhere. Thank you!